The first topic that we're going to talk about on the evaluation front is this topic of data transformations. Let's take another closer look at the values that we're trying to predict, our target values, the property prices. Check out this histogram. This is what we plotted earlier. Now, what we see here is that there are quite a few very, very expensive properties on the right-hand side of this graph. There's a bunch of properties in the right tail of this distribution. And here's what a normal distribution looks like in comparison. The normal distribution has very, very few occurrences in the tails. And here's the thing, having more data points in one of the tails is called a skew. Our distribution of house prices is skewed to the right. Now, we can actually put a number to the skew. We can measure the skew of our target values. Let's add a markdown cell to this section and commemorate what we're going to do. We're going to write down data transformations. There we go. To calculate the skew of our target values, all we have to do is grab our price series, data square brackets, price, put a dot after it, and call the skew method. Hitting Shift Enter, we see that this skew is 1.1. Now, what does that mean? And how does that compare to a normal distribution? Well, a normal distribution is completely symmetrical, right? The right tail and the left tail are exactly the same size. So the skew of a normal distribution is equal to 0. And this leads me to think that there's something that we can try to improve our model. We can try transforming our price data and then running our regression. Now, what do I mean by transforming our data? Well, a transformation would be something like multiplying all the prices by 2 or dividing all the prices in half. A transformation would be applying some sort of calculation to all the prices in the dataset. However, dividing or multiplying our prices isn't the transformation that I have in mind. I want to do something to our prices that will shift our distribution. I want to do something that will affect our large house prices in the tail more than the rest. And to accomplish this, I will use a log transformation on our property prices. And so that means that if one of the target values, one of the prices, is equal to the value 7, then the log of this price is equal to 1.95. And you can calculate this simply by grabbing a calculator and using the ln function on that thing. But here's the interesting part. If a property price is listed as 50, so some of the highest values that we have in our data set, then the log price of this property would now be equal to 3.91. Thus, what the log transformation achieves is you get a small change of around 5 in the small price of 7, but you get a large change of around 46 for the large values in the dataset. Now, a very reasonable question to ask is, why does this matter? Why should you care? Well, we have to remember that what we're doing here is we're fitting a linear model to our data. So say we have some data that's distributed like so, distributed like this. If you were to try to fit a line to this data, a straight line, you don't tend to get a very good fit. But if you were to transform this data using the log transformation, then those blue dots would line up like so. And then you could fit a linear regression very, very easily, and you'd get a very, very good fit. So in other words, based on the skew that I've seen in the distribution, I want to try transforming our data and then fitting the linear regression. Now, one thing I'm noticing is I've actually got a typo here in my notebook title. This should read multivariable regression, not multivariate regression. There we go. Okay, so how do we apply a log transformation to our target values? Well, what we could do is to write something like from math import log and use the log function from the math module. However, this log function from the math module doesn't particularly enjoy being applied to an entire data series. Lucky for us, NumPy actually solves this problem for us. We can access the log function through NumPy. So np.log parentheses data square brackets single quotes price will transform our entire series of prices into log prices. I'm going to create another variable called y_log and set that equal to the output of NumPy's log function. Let's take a look at what y_log actually looks like. So y_log.head will show me the first few values, and they look something like this. And y_log.tail will show me the last couple of values, and they look something like this. So what we saw here was that this log transformation was applied successfully to the entire data series. We now have the logs of the property prices stored in a variable called y_log. Now, I can already hear you asking the question, well, where can we see the benefit of using log prices? And I think that's a really, really good question. We're going to look at three things. First off, let's look at the skew of the distribution of the log prices. So y_log dot skew parentheses will output minus 0.33. So that's nice. With a skew of minus 0.33, we're a lot closer to 0 than with a skew of 1.1. But what does this distribution look like graphically? Let's pull up our old friend sns.distplot parentheses y_log plt.title parentheses f single quotes log price with skew curly braces y_log dot skew next line plt.show. Here we're using Seaborn's displot function, and we're feeding in our log prices. We're going to give this little chart a title, and as an argument, we're feeding in an f string. I've misspelled price, so I'm going to fix that now. So our f string will take this part here that's in between the curly braces and actually calculate the skew. So this bit here will show minus 0.33. And then we're showing our chart. Let me hit Shift Enter. Let's see what this looks like. Voila. Now this distribution already looks a lot more symmetrical. And with that skew being a lot closer to 0, it also definitely is a lot more symmetrical. We can actually see this difference very, very clearly when we look at these two charts side by side. Now, I'd say this transformation worked really, really well from this point of view. Now, having looked at the skew, a good question is, well, can we visualize how this transformation makes our data more linear graphically? And the answer is yes, but it's a little hard to see. It's a little hard to make out on real data. You're just not going to get a graph that's like clear as day as this kind of hypothetical example. The biggest difference that you'll actually be able to spot just by inspecting it is on a plot of property prices versus the LSTAT feature. So using Seaborn with SNS and then .lm plot will give us our scatter plot with a regression line. And this scatter plot is going to have, on the x-axis, it's going to have lstat, the lstat feature. On the y-axis, with y equals as the second argument, it's going to have price. So we're going to compare our non-log prices and then the log prices afterwards. As a third argument, we're going to give our data. As a fourth one, we're going to say size equals 7 to make that thing a bit larger. As the fifth argument, I'm going to add some transparency to our data points with scatter underscore KWS equals, and then a dictionary, curly braces, single quotes, alpha, colon, 0.6. And then I'm going to add a colored regression line. So that I can do with line underscore KWS is equal to another dictionary, single quotes, color, colon, and I'm going to go for dark red. Dark red. There we go. I'm going to spread this over 2 lines, and then I'm going to go with plt.show and hit Shift Enter. Ta-da! This here is a larger version of something we've already seen in our pair plot a little bit earlier. And one thing that you can see is that this regression line doesn't fit the data maybe as well as it could. Just by looking at this, we can see that the relationship between lstat and price might not be a linear one. But what about our log prices? Let me take this cell, copy it, paste it, and then I'm going to change the color to cyan. And what I'm going to do now is I'm going to create a new variable, a new data frame. Call it transformed underscore data. And I'm going to set it equal to, say, features, which we've created up here. Our features variable was equal to our data frame minus that price column. So we're going to reuse that down here. And then what we'll do is we're going to add another column to the transformed underscore data frame. And we're going to call that column single quotes log underscore price, all caps. And that's going to be equal to y underscore log, which we've created up here. So we can reuse this variable as well. Okay, so we've created a new data frame, and it has all the features and our log price. And in our lm plot function, we're going to feed in the transformed data. And on the y-axis, we're going to be plotting log underscore price. So the log price column from the transformed data frame. So let's hit Shift Enter and see what we get. Ta-da! So here's our log price versus lstat. And here is our untransformed normal price versus lstat. Now, we can see somewhat of an improvement based on this particular scatter plot, but trying to spot the differences visually against all the individual features isn't really all that useful. What we really want to do is we want to rerun our regression and see the combined effect of using log prices instead of the standard prices. The thing to note is that now we've got a different model, right? We're actually going to be changing our regression model. We're going to be using log prices instead of normal prices. So our previous equation looked like this, and our new equation will look like this. And because it's a very different model that we're using, all the theta values will in fact change. And the interpretation will also be taking into account that a unit change in, say, distance or the number of rooms now reflects the change in the log price. So that's just something to be aware of. Let's see this in action. I'm going to come up here in our notebook where we were splitting our data set, and I'm going to copy this cell. And then I'm going to paste it down here. The first thing I'm going to do is I'm going to change this line of code. I'm going to say prices is equal to np.log parentheses data square brackets price. So here we're using log prices now when it comes to shuffling and splitting our data set. The next thing I'm going to do is I'm going to delete this line of code, and I'm going to come back up here where we're running our regression. I'm going to copy these cells, come down here, paste them in, delete this comment, and then this cell here, I'm going to change to markdown, put 2 hashtags there, and I'll write down regression using log prices. And now I'm going to hit Shift Enter here. And this is the output that we'll get. So the question is, how do we interpret this? Let's look at the R² values first. The R² on our training data is 0.79. This is an increase actually from before. Before we had 0.75. And we also see an increase on the testing data. Here, the value went from 0.67 to 0.74. So the performance of our model improved on both counts. And based on this, it makes me think that our little data transformation experiment was a success. Reducing the skew in our distribution of target values allowed us to improve our model. And as a result, we have a higher R² and a better fit. But I also said that the interpretation of the parameters has changed. Previously, the coefficient for the Charles River dummy variable was around 2. So people were willing to pay $2,000 more to live close to the river. Now the coefficient on the Charles River dummy variable is 0.08. In order to figure out how much more people are willing to pay to be close to the river according to this model, what we have to do is reverse the log transformation. Because not even mathematicians think in log prices when they go to the supermarket. So let's see what this value translates into using actual dollar prices. I'm going to copy this whole thing, and in this cell down here, I'm going to add a comment, Charles River property premium. And in this cell, I'm going to reverse the log calculation so we can see what the dollar value is. Now, as a math refresher, the way that the log transformation worked was we took the log of our prices. So if the price was 12, then the log price would be equal to 2.485 approximately. To reverse this transformation, we have to raise Euler's number, which is approximately 2.7, to the power of 2.485. And then we get back our starting log prices. So this is how we're going to reverse that calculation. We need to get hold of this number E. And we can get hold of this number E through NumPy. np.e will give us access to this irrational number. And with times, we can raise E to the power of 0.080475, our coefficient. Now we can see how to interpret this coefficient. And what our new model is telling us is that people are willing to pay approximately $1,084 more to live close to the river. Okay, so that was quite a big lesson, quite a lot going on. Through our process of transforming our target values, we've created a whole new regression. And this new and improved regression fits our dataset even better. But because we're now working with log prices in our model, our interpretation of these coefficients has also changed. In order to get back the changes in the dollar values, we have to reverse the log transformation when it comes to actually interpreting the meaning of our coefficients. And speaking of coefficients, in the next lessons, we're going to be looking at them in more detail. We're going to be evaluating our coefficients and looking at their significance, their p-values. I'll see you there.